In this lesson, we are going to look at wave amplitude and wave frequency, and this applies to all waves. And we're also going to look at sound waves in particular and the relationship between frequency and pitch in sound waves. Let's begin by considering an experiment. If you look at the apparatus shown in the diagram, we begin with a signal generator. A signal generator produces an electrical signal which has a current which goes back and forth, first one way then the other, and it causes the loudspeaker cone to vibrate in and out to produce a sound. So the first thing that happens then is that the signal generator causes the paper cone of the loudspeaker to vibrate. That in turn causes the air to vibrate. So the vibrations are carried through the air and they go off in a whole sort of number of directions spreading out, and some of them are detected by the microphone. So the sound waves travel as a longitudinal pressure wave to the microphone, and the microphone detects them. These vibrating air molecules then are detected by the microphone, and the microphone converts the to and fro motion of the air molecules into another electrical signal, which again has electric current going one way then the other, corresponding to the to and fro motion of the molecule's vibration. You'll notice that the microphone is connected via wires to a device called an oscilloscope. And an oscilloscope is like a kind of sophisticated voltmeter really, but it doesn't give you a digital display, it gives you a graphical display. So what happens is that the oscilloscope shows a wave trace on its screen, something like this. So first of all, if you look at the longitudinal wave itself, that's the sound wave traveling through the air. Notice that you can see compressions where the air molecules are sort of squashed together, and decompressions where they're more spread out. So that's the sound wave itself. Now what's actually shown on the oscilloscope looks like a transverse wave, and in terms of how we look at it, it is a transverse wave, but remember the sound wave itself is longitudinal. It's simply represented on the oscilloscope screen by this transverse wave. So if you look at the central compression in the longitudinal wave, that black line takes you down to a crest. So a crest on the oscilloscope trace corresponds to a compression in the actual sound wave. Correspondingly, if you look at the decompression just to the right of that and follow your eye down to the transverse wave below, you'll see it corresponds to a trough. So the wavelength of the actual sound wave, the distance between two adjacent compressions, is represented on the oscilloscope trace by the distance between two adjacent crests. The louder the sound, the bigger the amplitude, and we'll say more about that shortly. So to sum up then, a compression in the sound wave corresponds to a crest on the oscilloscope trace, and a decompression in the sound wave corresponds to a trough on the oscilloscope trace. Okay, let's focus now on the amplitude of these sound waves. If you look at the upper trace, this is the sort of trace you would see on the oscilloscope when we have a loud sound. You'll notice that a loud sound has a high amplitude. The red arrow shows the extent of the amplitude. The amplitude, remember, is measured from the line of zero disturbance, the line of CAM, right up to the top of a crest. Alternatively, an amplitude could be represented by a line going from the line of zero disturbance down to the bottom of a trough. The most important point then is that loud sounds have high amplitude, and so they produce a trace with these tall crests and tall troughs. It's worth also bearing in mind that a loud sound, as well as having high amplitude, therefore has high energy. So you need more energy to make a loud sound than you do to make a quiet sound. In the trace below, you'll see that is a quiet sound and it has low amplitude. Look at the size of that small amplitude. That's quite a quiet sound. There again is the amplitude. Quiet sounds, of course, have low energy, just as loud sounds have high energy. So there you are, quiet sounds have low amplitude and they produce a trace on the oscilloscope, just like that. Finally, in this lesson, we are going to look at the frequency of sound waves and discover the connection with pitch. Well, if you look at the diagram, you'll see three different waves, and those wave trains, that's the series of crests and troughs, have all been produced in a time of 1 second. Okay, so if you look at the top one, the red one, you can see we've got what, 1, 2, about 3 whole waves produced in a second there. The blue one in the middle looks like we've got about 1, 2, 3, 4, 5, about 6 whole waves produced in a second there. And then in the bottom one, even more than 6 waves produced in a second. So important to remember then, each of these 3 different waves took 1 whole second to make. Well, the red wave at the top is said to have low frequency. It means that not that many waves are produced in a second. And it turns out that low frequency waves, if they're sound waves, have a low pitch. Now, a low pitch just means a low note, so the sort of note that a double bass would produce on its lower strings. Okay, so low frequency in a sound wave means low pitch. A bass voice, for example. On the other hand, the high frequency note at the bottom, where there are lots of waves produced in a second, produces high-pitched notes. Sort of instrument that would produce highly pitched notes would be something like a piccolo, and there's one shown. So, key points to remember: low frequency means low pitch, not many waves produced per second, and high frequency means high pitched, lots of waves produced per second. And we'll consider an equation for frequency in the next lesson.